So in this session on signals and systems, we are going to start the study of frequency spectrum of signals. In order to understand this easily, we will first start with a very simple signal which consists of a single cosine component. So let us first of all write the equation for this. So we can write xt is equal to a cos of omega naught t plus theta. So when we look at this equation, there are three important parameters you can find. One is the amplitude of the cosine wave, second is its frequency, and the third is its phase angle. Now, when we want to plot the frequency spectrum of such a signal, what we do is we express it by using two plots. One is you plot omega on the x-axis and amplitude on the y-axis using a line plot. So in this case, there is a single frequency. So you will get a single line at omega equal to omega naught, whose height corresponds to the amplitude A. And the second plot that we can make is that of frequency on the x-axis and phase angle on the y-axis. And again, you will get a single line. So let us see this. So this plot is called as the amplitude spectrum, in which we have plotted omega on the x-axis, amplitude on the y-axis. And since there is a single frequency in this particular signal, at omega equal to omega naught, you get the amplitude which is equal to A. Then you make a plot of omega versus phase and you get one line, that is at omega equal to omega naught, the phase angle is theta. Okay, so that this is called as the frequency spectrum of the cosine wave, that is these two plots together. So one is called as the amplitude spectrum, as we said, and the other is called as phase spectrum. Okay, let us consider a slightly more complicated signal in which you got a signal which is addition of two cosine waves. So you got a1 cos of omega 1 t plus theta 1 plus a2 cos of omega 2 t plus theta 2. So it is clear simply by the inspection of this equation that there are two frequency components, omega 1 and omega 2. And if you sketch the amplitude spectrum, you will get two lines. At omega 1 you will get a1, at omega 2 you will get a2. And similarly for the phase spectrum, you will get two lines. At omega 1 you will get theta 1, and at omega 2 you will get theta 2. So let us look at these spectrums. So this is the amplitude spectrum. At omega 1 you got a1, at omega 2 you got a2. In this particular example, I am just assuming that a2 is greater than a1, but it need not always be so. It all depends on the nature of the signal. Similarly, in the phase spectrum, at omega 1 you have theta 1, and at omega 2 you have theta 2. Okay. Next, so in this case, we were using cosine functions in order to sketch. Now the cosine function can also be expressed in terms of an exponential. So you can plot the spectrum slightly differently by using the exponentials, and we'll see the reason for doing it a little later. So to plot this, cosine wave is expressed in terms of complex exponentials. So we got suppose we have a signal which is xt is equal to a cos of omega naught t plus theta. Then you can write this xt as a by 2 e raised to j omega naught t plus theta plus e raised to minus j omega naught t plus theta. This is a well-known equation, that is cos theta is e raised to j theta plus e raised to minus j theta divided by 2. So that is, using that equation we get this. Let us expand this. So we get a by 2 e into e raised to j theta into e raised to j omega naught t. That is the first term. And the second term is a by 2 e raised to minus j theta into e raised to minus j omega naught t. Now e raised to j omega naught t can be considered as a rotating phasor in one direction, and e raised to minus j omega naught t can be considered as a rotating phasor in the opposite direction. And you could say mathematically that this corresponds to positive frequency and this corresponds to negative frequency. Understand that this is only a artificial mathematical concept. Physically, of course, you cannot have a negative frequency. However, what we have done basically is we have considered two complex quantity and added them in order to get a real signal. That is what we have done. And that is why you get the concept of positive and negative frequencies. All right. Now this we can write in a slightly different fashion, making it more compact. So this is a by 2 e raised to j theta is written as x1, and a by 2 into e raised to minus j theta is written as x of minus 1. So it's easy to see that x1 is x into e raised to j theta, x2 or x of minus 1 is x into e raised to minus j theta, and what is x? X clearly in both cases is a by 2, and you can see that x1 and x of minus 1 are complex conjugates of each other. x1 is equal to x of minus 1 star, the complex conjugate. Okay. So once you express your cosine wave by using exponential functions rather than retaining the original form, you can sketch the spectrum slightly differently now. So in this case, you will see that x1 and x of minus 1 are complex quantities, and it will have magnitude as well as phase angle. So magnitude is a by 2 in both cases, whereas the phase angle in one case is theta, in the other case it is minus theta. So if you sketch this spectrum, you now get a double-sided spectrum, because we have introduced the concept of positive and negative frequencies. So at omega equal to omega naught, you get x, which is a by 2, remember, and at minus omega naught you again get x, which is also a by 2. So this is the amplitude spectrum, and understand that it is an even function of frequency. On the other hand, when you plot the phase spectrum, at omega naught you get theta, and at minus omega naught you get minus theta, which means that the phase spectrum that you obtain by using the exponential functions, using a double-sided spectrum, the phase spectrum is an odd function of frequency. Okay. Now what is the advantage of expressing cosine in terms of complex exponentials? So in many cases you will find calculations are somewhat simplified. To illustrate that, consider the mathematical calculation of products. So suppose I want to take the product of e raised to j theta 1 into e raised to j theta 2. In that case, this can be very easily obtained by summing theta 1 and theta 2. So you can see that by using complex exponentials, many a times the calculations are simplified. Similarly, if you want to add the two, you simply expand them as cos and sine functions and add the real parts and add the imaginary parts. So that is the reason. Of course, it doesn't mean that the trigonometric form is useless. It's quite useful in order to visualize the waveforms. So as far as the calculations are concerned, the exponential form is useful. It's easier in trigonometric form. You have to use trigonometric identities. However, trigonometric form is useful when you want to visualize the waveform. So you can see, for example, one part of the signal may be cosine wave of some frequency, and the second cosine wave may be double the frequency. It's easy to visualize how the signal will look like. Okay. Now, in this, when we started our discussion, we simply said that xt is known to be summation of number of cosinusoidal cosine waveforms. However, in practice, this is often not the case. The signal which is available to you is really available as a function of time. When it is available as a function of time, then how do you obtain the spectrum? That is the question. See, if it is available directly as a sum of cosine or sine terms, it's easy to see the frequency spectrum. But when that is not so, which is so in most of the cases, then how do you calculate the spectrum? So you have to use mathematical tools which are called as Fourier tools. And in order to see which Fourier tool we are going to use, let us look at the classification of the signals first. You can subdivide them into periodic and non-periodic types. Periodic signals, all of us are well known. Of course, the purest is sine wave, which means there is a single line. You don't have to do any calculation. But suppose you have a square wave, then for a square wave there will be fundamentals, number of harmonic components and so on, and you would like to calculate the amplitude and phase of these harmonic components. So that is one example. You can have a triangular wave and so on. So these are all examples of periodic signals, and the spectrum of these signals can be calculated by using a tool which is called as Fourier series, which we shall study next. What about non-periodic signals? So, for example, consider a rectangular pulse which occurs only once, and once it has occurred, afterwards it is zero, and before it occurs, the value is again zero, which means it's not periodic at all. Or you can have a random signal. For example, information carrying signals are often random, and theoretically you can say that they never repeat themselves, or they repeat themselves after infinite time, which is as good as saying that they don't repeat themselves. So they belong to non-periodic classes. These are two of the examples. So for periodic signals, you need to study Fourier series, and for non-periodic signals, you need to study Fourier transform. Now in this lecture, we are going to concentrate on Fourier series. So let us start with that. So first of all, let us consider a continuous time signal and consider the trigonometric form of the continuous time Fourier series. That is what we want to study. So consider a periodic signal with the period t. In that case, its fundamental frequency is omega naught, that is 2 pi by t. And then you can express xt as a sum of number of cos and sine waves. In fact, theoretically, infinite number. This a naught essentially corresponds to the DC component, and then you have number of cos components and number of sine components. For example, when n is equal to 1, you got a fundamental cosine component and also a fundamental sine component, and this will have an amplitude a1 and this will have an amplitude b1. Then when you consider n equal to 2, this is second harmonic and the corresponding amplitudes are different. The question now is how to calculate a naught, an and bn. A naught is basically a DC component and you can simply calculate it. Remember, DC component can be calculated by evaluating the area under the periodic signal over one time period and dividing it by the time period itself. That will give you the DC component, which we call as A naught. What about AN? AN can be calculated by performing this integration. And what does it involve? You take xt, and of course xt is known over one time period. Understand that this expression for xt is valid for any time. Here what we are saying is that the expression for xt is known over one time period, and using that expression and multiplying it by cos of n omega naught t and integrating and then multiplying by 2 by t, we get an. So an will be some function of n. So when you calculate a1, it will correspond to the fundamental frequency, a2 will correspond to the second harmonic and so on. And similar remarks go for b1, b2, etc. These are the coefficients of the sine wave. Now, one problem with this type of expression for the Fourier series is that it's not clear for a given frequency what is the amplitude and what is the phase angle. For example, you consider the fundamental. The coefficient of cos term is a1 and coefficient of sine term, which is also having the same fundamental frequency when n is equal to 1, is b1. So the question is, which is the amplitude? Is it a1 or is it b1? To resolve that, what we do is we combine this into another form which we call as the polar form, and it can be written like this. So c naught plus n equal to 1 to infinity cn cos of n omega naught t plus theta n. And it will be easy to show that c naught will be equal to a naught itself. Cn will be equal to under root of an squared plus bn squared, and theta n will be tangent inverse minus bn divided by an. So now there is no ambiguity. When n is equal to 1, that is the fundamental frequency, and the amplitude is C1, and the phase angle is theta 1. When n is equal to 2, it is the second harmonic, and the amplitude is C2 and the phase angle is theta 2. So now there is no confusion. Okay, so this is the polar form. So basically when you are using these trigonometric forms, what you have to do is calculate A0, AN and BN, and then by using AN and BN calculate CN and theta n, and then for various values of n you can plot the frequency spectrum, because the amplitude is known and the frequency and the phase angle is known. So this is simply an extension of the earlier examples that we studied, except that you have got large number of terms. There we had only 1 or 2 terms when we discussed, but the principle is same. Alright, so this is the trigonometric form. But as we explained in the case of simpler cases, here also exponential Fourier series is often useful because calculations are made easy. And its form is like this: xt is sigma n equal to minus infinity to plus infinity xn e raised to j n omega naught t. So understand that for every value of n, you got plus and minus term. So this will be x1 e raised to j omega naught t, and then x of minus 1 e raised to minus j. So when you combine them, you will get a real signal. So you got pairs. Now how do you calculate xn? Xn is simply calculated like this: 1 by t multiply xt by e raised to minus j n omega naught t, integrate over the time period t, and you will get xn. And this xn that you will get in general is going to be a complex quantity. So you can find its magnitude for various values of n, and you can sketch the magnitude spectrum or the amplitude spectrum, and for various values of n you can calculate the phase angle of xn, because it's a complex quantity, so it has a magnitude as well as phase angle. So you can plot the amplitude and the phase spectrum. As we have already said, the advantage of the exponential representation is that calculations are easy. So in our next session, what we'll do is we'll take an example and see what are the results of calculation of Fourier series, and we will also see a MATLAB program which will allow us to plot the amplitude spectrum and the phase spectrum. But for now, that's all.